The night should have changed everything. Opposition night, the moment astronomers had been waiting for, the alignment written into every observing schedule, the geometry that promised answers. Fury Atlas, the third confirmed visitor from another star system, reached the exact position opposite the sun in Earth's sky. This is the configuration that astronomy textbooks describe with quiet confidence. Shortest distance, cleanest sight lines, maximum reflected light. The mathematics was set. The telescopes were ready. Across 3 continents, coordinated teams locked instruments onto the predicted coordinates, exposures stretching longer than usual, detectors primed to catch every photon traveling across millions of kilometers of space. They waited. The light should have been there. It wasn't. The object remained dim. Not the expected dimness of distance. That's routine, manageable, anticipated in every observation plan. This was something else. A dimness that shouldn't exist. The geometry had improved exactly as predicted. The phase angle had dropped to near zero. Weather conditions were optimal. Every variable that controls brightness, sun distance, Earth distance, viewing angle, had shifted in the observer's favor. Yet brightness did not respond. The signal astronomers depend on to measure size, surface properties, and activity stayed suppressed, stubbornly beneath the threshold that decades of experience and refined models had promised would be crossed. And in the carefully worded language of international observational circulars, a new kind of tension emerged. Not the usual request for more data or confirmation needed. Something sharper. More unsettling. The measured brightness does not match what opposition geometry should have delivered. This is not a story about losing an object in the vastness of space. This is about an object that is there, precisely where the equations say it should be, but refusing to behave the way reflected sunlight is supposed to behave. Opposition is the observer's advantage, the moment when the universe briefly aligns in our favor. Distance shrinks. Angles optimize. Light that would scatter away at other geometries scatters back toward Earth. For weeks, the global astronomy community had been marking calendars, scheduling telescope time, coordinating across time zones for this window. Earlier observations had been frustrating, faint detections at the edge of noise, ambiguous rotation signals, photometry contaminated by poor phase angles and greater distance. Opposition was supposed to clarify. It was the night that should have rewarded months of patience with clean data, tighter constraints, maybe even a brightness surge, if the surface had the right texture, or if a lingering dust coma was still catching sunlight. Instead, the numbers came back wrong. Magnitude stayed low. Flux stayed weak. And as data sets were compared across observatories, different telescopes, different filters, different hemispheres, a realization moved quietly through email threads and Slack channels. Something about this interstellar visitor's light has changed. Or perhaps it was never what the first measurements suggested. Either way, the object is not playing by the rules. And opposition, the night that should have solved the mystery, has instead made it darker. If you enjoy this unfolding mystery, subscribe for more Beyond the Solar Veil cosmic documentaries. To understand why still dim matters, you have to understand what opposition actually guarantees and what it does not. Opposition is not magic. It doesn't make objects intrinsically brighter. It shifts the geometry in ways that should improve what we see, if the object obeys the standard rules of reflected sunlight. Brightness depends on 2 distance terms and 1 angular term. First, how much sunlight reaches the object, which falls off with the square of its distance from the sun. Second, how much of that reflected light reaches Earth, which falls off with the square of Earth's distance to the object. Third, the phase angle, the sun-object-observer triangle, which controls how much of the illuminated hemisphere we see and how efficiently dust or surface grains scatter light back toward us. At opposition, Earth and the object are nearly aligned with the sun behind us, minimizing phase angle. For many solar system bodies, this configuration triggers subtle brightening effects. Shadows disappear, surface roughness scatters more light retroward, and the so-called opposition surge can add tenths of a magnitude to the observed brightness. For active comets with dust comae, the story is more complex. Forward scattering dominates at large phase angles, but opposition can still improve visibility by maximizing the illuminated cross-section we observe. Astronomers don't guess at brightness. They calculate it. They build predicted magnitude curves from orbital elements, assumed albedo, estimated size, and empirical phase functions borrowed from similar objects. Those curves are testable promises. They encode expectations. And when an object reaches opposition, the curve should show a local minimum in magnitude, meaning a peak in brightness, because distance is near its minimum and phase angle is near zero. For 3I Atlas, that minimum was predicted. Observing schedules were built around it. Exposure times were optimized for a target magnitude that reflected the combined advantages of geometry. But the measurements came back fainter. Not by a little. Not within the uncertainty of the photometric model. Fainter in a way that suggested either the phase function was behaving unusually, scattering light less efficiently than expected, or the object's reflective surface had physically changed since earlier observations were used to anchor the model. The curve didn't just miss the prediction. It missed in a direction that raises questions about matter, not math. Phase angle is more than geometry. It's a fingerprint of surface physics. How light scatters off an object depends on grain size, particle packing, surface roughness, porosity, composition, and whether you're looking at bare rock, regolith, or a suspended cloud of micrometer-scale dust. At low phase angles, near opposition, many solid surfaces show a brightening because shadows cast by surface irregularities shrink and light scatters preferentially back toward the source. This opposition effect is well documented for asteroids and has been measured across hundreds of near-Earth objects. But 3I Atlas is not a simple rocky body. Earlier data suggested the presence of a faint coma, a diffuse envelope that implies some level of volatile-driven activity or dust release. Cometary coma behave differently. They can forward scatter strongly at high phase, making comets brightest when viewed from the side rather than head-on. So opposition, for an active body, doesn't always guarantee a brightness boost. It can actually reduce visibility if the coma's scattering properties favor non-zero phase angles. But that's a known effect. It's modeled. It's anticipated. What's unsettling here is that the dimness appears stronger than even a forward scattering coma would predict, unless the coma has thinned significantly, or the grain size distribution has shifted, or the scattering cross-section has collapsed in a way that timing alone, reaching opposition, can't explain. Astronomers look for mismatches between predicted magnitude and measured flux across multiple observation epochs and phase angles. If an object is consistently fainter than the model at all phases, the likely culprit is size or albedo. The object is smaller or darker than assumed. But if it's fainter specifically at opposition, while earlier high-phase observations were closer to predictions, that's a phase function problem. It suggests the way the surface or coma scatters light is not behaving according to the empirical templates borrowed from comets or asteroids. It could mean the surface is unusually rough, trapping light in pits and voids. It could mean a thin dust layer has settled or dispersed, changing the optical depth. It could mean the material composition favors absorption over scattering at visible wavelengths. Or it could mean the activity that created the coma in earlier observations has shut down, and what remains is a bare, low albedo nucleus that was always dim, but was temporarily masked by reflective dust. This is not just photometry. This is material science written in magnitudes, an encoded description of matter we cannot touch, sampled only by the faint echo of sunlight it scatters into our detectors. Before the anomaly becomes physics, it has to survive an audit. If an object is unexpectedly dim, the first obligation is to confirm the dimness is real, not an artifact of calibration, sky conditions, or observer error. The integrity of the measurement must be tested against mundane explanations that have nothing to do with the object and everything to do with the process. Photometry is precise, but it's not automatic. Background stars can blend with the target, inflating or deflating the measured flux depending on their brightness and proximity. Air mass, the thickness of atmosphere the light passes through, affects extinction differently across filters and changes as the target rises or sets. Photometric zero points, the calibration constants that convert detector counts into magnitudes, vary with weather, telescope alignment, and filter age. Systematic biases creep in through flat field corrections, cosmic ray removal, and the choice of comparison stars used to anchor the photometry. Each of these is fixable, but only if recognized. Each can quietly distort a magnitude by a few tenths, which at the faint end is the difference between detection and non-detection, between confirming an anomaly and dismissing it. So the community runs the checks. Multiple observatories, using different instruments, different filters, different photometric pipelines, target the same object at similar phase angles and compare results. If one site measures dimness and another does not, the anomaly collapses into method. If all measure dimness within their respective uncertainties, the signal becomes robust. For 3i Atlas at opposition, the consistency emerged slowly but clearly. Independent teams, working in different photometric bands, Johnson 4S, SDSR, even some near-infrared attempts, reported magnitudes fainter than the predicted opposition brightness. The scatter between measurements was normal. The offsets were not. The dimness reproduced. And that reproducibility is the forensic moment when a surprise stops being a possible mistake and starts being a physical clue. Astronomy is a discipline that distrusts surprise. It takes systematic agreement, cross-validation, and the elimination of convenient alternatives before a faint signal is allowed to mean something. That process happened here, quietly, and the dimness survived. Opposition was also supposed to clarify the light curve, the pattern of brightness variations over time that reveals rotation. Many small bodies are not spherical. They're elongated, irregular, tumbling through space, and as they rotate, they present different cross-sections to the Sun and to Earth. That creates brightness modulation. The object brightens when a broad face is illuminated and visible, and dims when we see it edge on. The amplitude of that modulation and its period encode the shape and spin state. Earlier observations of 3A Atlas hinted at possible rotational variability, but the data were marginal. Short observing arcs, low signal-to-noise, ambiguous periodicity. Opposition, with its improved brightness and longer nightly visibility windows, should have been the moment to nail down the rotation period, confirm the amplitude, and use that information to constrain the object's axial ratio and orientation. But the expected clean peaks in the light curve either flattened, arrived muted, or failed to appear at all in datasets that should have been sensitive enough to detect them. That absence, or attenuation, of rotational modulation is itself information. If the light curve has lost structure, several physical interpretations become possible. The spin state could have changed, either slowing due to torques from asymmetric outgassing, or entering a tumbling mode where the rotation axis itself precesses, smearing out periodic signals. The pole orientation could have shifted, altering which parts of the surface are illuminated and viewed during each rotation. A dust veil, if still present, could smooth out brightness variations by scattering light more uniformly than the bare nucleus beneath. Or, and this is stated carefully without drama, the object could have fragmented into multiple smaller components, each contributing to the total brightness, but no longer rotating coherently, diluting the periodic signal into noise. If the light curve has lost its structure, the possibility exists that the object has lost structural coherence as well. That's not a claim. It's a hypothesis that fits the data, and one that can be tested with higher spatial resolution or deeper imaging to search for elongation, multiplicity, or a widening brightness profile. Dimness at opposition invites a different kind of investigation, not what the object is doing, but what has stopped happening. Brightness requires a reflective surface or a scattering medium. If either degrades, brightness falls. A dust coma, for instance, can thin rapidly as volatile ices deplete. Water, carbon monoxide, carbon dioxide, depending on heliocentric distance and thermal history. As sublimation slows, the production rate of dust grains drops. The existing coma doesn't freeze in place. It disperses under radiation pressure and the weak gravity of a small nucleus. The scattering cross-section shrinks. The object dims. This process can be abrupt if the last surface volatiles are exhausted, or if a thin ice layer seals beneath a refractory crust that insulates the interior. Fresh cometary surfaces are often brighter than aged ones, because sublimation continuously exposes clean ice and fine dust. But once activity ceases, that surface darkens, mantled by non-volatile residue, carbonaceous material, or silicate grains that absorb visible light efficiently. The transition from active to dormant can produce a brightness drop steeper than distance alone predicts, and it can happen faster than orbital mechanics would suggest. Microfragmentation offers another mechanism, one that seems counterintuitive, but is observationally documented. When a small body breaks apart, the immediate result can be a brightening, fresh surfaces, more total area, enhanced dust release. But if the fragments are small and disperse quickly, the brightness per unit sky area drops. The total light gets spread over a larger angular region. Surface brightness falls. Against a noisy sky background, diffuse emission is harder to detect than a compact point source, and the object can effectively vanish photometrically, even though the mass remains. This isn't explosion, it's dispersal. And for an interstellar object, subject to thermal stresses from its first close passage by a star in potentially millions of years, structural fragility is plausible. Rapid heating and cooling, volatile pressure buildup, and spin-up from asymmetric outgassing can all contribute to tensile failure. The observational signature would be subtle. A slight elongation in high-resolution images, a broadening of the point spread function, or a decline in central condensation, the degree to which brightness is concentrated at the photocenter. At opposition, when seeing conditions are often best and integration times longest, such signatures should be detectable if present. Their absence doesn't rule out fragmentation. It constrains the timescale and the fragment separation velocity. There's also the question of thermal history and its delayed effects. 3. Atlas perihelion, the closest approach to the Sun, weeks or months before opposition, depending on the specifics of its hyperbolic orbit. That's when solar heating was strongest, when any volatile-driven activity would have peaked, when the object would have been shedding dust most vigorously. But activity doesn't shut off instantly when heating declines. There's a lag. Internal heat conducts slowly through porous material. Subsurface ices continue sublimating even as the object moves outward, until the surface temperature drops below the sublimation threshold, or the ice layer is exhausted. The brightness we see at opposition reflects conditions established earlier, activity that may have already ceased, dust that may have already dispersed, structural changes that occurred during perihelion passage, but only became visible later as the coma thinned and the bare nucleus emerged. In that sense, opposition is not a snapshot of the present. It's a delayed readout of the object's response to past heating. And if that response included an activity shutdown, opposition becomes the moment we see the aftermath, not the event. There's also an external angle to consider, one that widens the frame beyond surface properties and rotation, the space environment itself. Solar wind. The continuous outflow of charged particles from the Sun interacts with small bodies in ways that are subtle but measurable. For an object with a tenuous coma, even a faint one, solar wind can shape the dust distribution, charge the surface, and alter how particles scatter light. Electrostatic forces, if strong enough, can loft fine dust off a low-gravity surface, creating a temporary brightness enhancement, or, conversely, clump particles into aggregates that scatter less efficiently. Plasma interactions can also produce non-gravitational forces, small accelerations that don't show up in purely gravitational orbit fits but accumulate over time, slightly altering the object's trajectory, spin, and orientation. If the orientation presented at opposition differs from what earlier astrometry implied, the illuminated cross-section changes, and so does the observed brightness. This isn't spectacle. It's the quiet reality that interplanetary space is not empty, and that objects moving through it are subject to forces and interactions that don't respect our simplified geometric models. Non-gravitational accelerations, when detectable, appear as small residuals in orbital solutions, deviations from a purely Keplerian path that require additional force terms to fit the astrometry. For active comets, these are usually attributed to rocket-like jets from asymmetric outgassing. But even for inactive or minimally active bodies, radiation pressure and solar wind drag can produce measurable perturbations. especially for objects with low mass and high area-to-mass ratios. If 3I Atlas has experienced such forces, its orientation at opposition, the angle at which we view its potentially elongated or irregular shape, might differ from what a purely gravitational extrapolation would predict. That orientation mismatch could reduce the effective cross-section, dimming the object without any change to its intrinsic surface properties. The geometry improved on paper, but the geometry in practice, accounting for torques, precession, and spin axis drift, may have shifted the object into a less favorable aspect. Dimness in this interpretation is not absence. It's a rotated presence. The object is still there, still reflecting sunlight, just not from the angle we expected. Looking forward, the observational window for 3I Atlas is closing. Opposition offered the best geometry, but as the object continues outbound on its hyperbolic trajectory, it will recede from both the Sun and Earth, dimming further regardless of any intrinsic changes. Within weeks, it will fade below the detection limits of most ground-based surveys, visible only to the largest apertures under optimal conditions. Follow-up observations are already constrained by magnitude limits, sky brightness, and the object's position relative to the ecliptic and galactic plane. The Vera C. Rubin Observatory, when fully operational, will detect future interstellar visitors earlier and track them longer, building a statistical sample where currently we have only individual enigmas. The James Webb Space Telescope, with its infrared sensitivity, might catch thermal emission from small, cold nuclei, even when reflected visible light has faded, offering a complementary dataset that reveals size and temperature independent of albedo. But for 3 Atlas specifically, the data collected around opposition may represent the last high-quality photometry we obtain. The investigation doesn't end with a conclusion. It ends when the light runs out. What remains is not a solved mystery, but a better defined one. Opposition was supposed to clarify, supposed to reward the patience and coordination of observers with cleaner signals, tighter constraints, resolved ambiguities. Instead, it delivered a contradiction. The alignment was perfect, the instruments were ready, the mathematics was confident, yet the object stayed dim. That outcome forces a recalibration. Either the object's scattering properties are unusual, suppressing the expected opposition brightness through phase function behavior we don't yet understand, or its surface has transformed in ways that earlier data, collected at different phases and distances, could not predict. Or the structure itself has changed, fragmented, mantled, reoriented, or stripped of the reflective dust that made it visible to begin with. Each interpretation is consistent with the data we have. None can be definitively ruled in or out without measurements. We no longer have the sensitivity to collect. Interstellar visitors are rare not only because they're uncommon, but because they arrive carrying physics we haven't practiced. Our models of brightness, phase functions, and activity are calibrated on solar system objects, comets that return, asteroids we've tracked for decades, surfaces shaped by 4 billion years under this sun. But an object from another star has a different history. It formed in a different protoplanetary disk, orbited under different stellar radiation, survived a different sequence of collisions and thermal cycles, and crossed interstellar space under conditions. Cosmic ray exposure, extreme cold, isolation from stellar wind that no local object has experienced. When we try to predict its brightness, we borrow models from objects that are only superficially similar. And when those predictions fail, the failure is not ours. It's information. It's the object teaching us that our categories are incomplete, our phase functions are parochial, and our assumptions about how small bodies behave are contingent on a sample size that, until recently, was entirely local. Opposition offered the best geometry the sky can give. The sun, earth, and object aligned. The phase angle dropped near zero. The distance reached its minimum. The viewing window was optimal. Yet, the brightness did not arrive. That absence, or suppression, of the expected signal is not a failure of observation. It's a message encoded in magnitudes, written in the language of reflected light, and it tells us something about the nature of matter moving between the stars. What it tells us precisely remains uncertain. Surface transformation, activity collapse, scattering anomaly, structural fragmentation, environmental interaction, along its outbound trajectory for follow-up data to resolve the ambiguity. The mystery survives opposition, survives audit, survives the best efforts of coordinated observing campaigns and careful photometric reduction. And that survival is, in its own quiet way, the story. Not what we learned, but what we couldn't learn. Not what the object revealed, but what it withheld. Not the light that arrived, but the light that didn't, and the patient, uncertain silence that remains.